Welcome to Microsoft Research Summit 2021. Today, I'm very glad to share our recent work, Focal Attention for Vision Transformers. Nowadays, transformer with self-attention mechanism has become a new norm in natural language processing. From the earlier small model like AMO to recent giant model like GPT-3, we have witnessed significant improvement in NLP. This significant improvement does not only occur at NLP, it also significantly affects the vision and language domain since 2 years ago. We can see tremendous works like Wilbert, XMERT, and the work from our own group, Oscar and Wimber, to most recent CLIP from OpenAI. All of these works are using transformers as a basic building block. Currently, we are also observing a clear trend of applying transformers to pure vision problems. At the beginning, people usually plug self-attention layers to convolutional neural network, but nowadays, many works replace convolutional neural network with transformers completely. On vision tasks, we have noticed the vision transformers and its variant beat the convolutional neural network counterpart with large margin. So, a natural question is, what makes VRT work? There are many potential reasons behind. First of all, vision transformer can model long-range interactions flexibly. On the left side, we can see convolutional neural network captures the local structure layer by layer hierarchically. In contrast, the vision transformers on the right side model the patch interactions globally at each transformer layer. Besides the long-range interactions, self-attention is more dynamic than convolutional neural network. It can not only model the local interaction for the grid input as convolutional neural network. It can also model the interaction for the visual input at arbitrary distributions noted by the gray blocks. Moreover, vision transformers have proved to have low-level floor but higher ceiling than CNN. With sufficient data augmentation and regularization, vision transformers can outperform convolutional neural network across different settings, as demonstrated by these two tables. Finally, many works have shown a good scaling trend for vision transformers in terms of model size and training data scale in both supervised setting and self-supervised setting. Despite the success of vision transformers in various settings, it's still a challenge to model long-range interactions for high-resolution input, which are very important for dense visual captions such as object detection, semantic segmentation. More specifically, how to cope with quadratic complexity of self-attention and how to achieve the best of both worlds to account both locality and globality. With this in mind, we propose the focal attention, a new attention mechanism towards efficient local global interactions in vision transformers. There are two main motivations behind our approach. First, vision transformer is good at long-range interactions, but not good at coping with high-resolution inputs. So, in convolutional neural network, multi-scale hierarchy has been applied to cope with this issue, as shown on the right side. Likewise, we can also adopt a multi-scale hierarchy for vision transformer, as shown on the left side. However, hierarchy and multi-scale are not enough to cope with this issue. Even though we use a multi-scale strategy, it is still difficult to model the global interactions for low-level, high-resolution feature maps. In NLP, there are a number of works coping with this long sequence by proposing local and sparse self-attentions. However, the local and sparse self-attention is not enough. We need both short and long-range self-attention to model the visual input. Based on this, we propose focal attention. As you can see here, the focal attention can both model short and long-range interactions. Differently, it achieves this by fine-grained attention locally and coarse-grained attention globally. As you can see, focal attention has a much larger receive feed than regular self-attention using the same number of tokens from the right side figure. This figure describes how focal attention works. Given the feature map at the left side, it can extract the fine-grained tokens which are closest to the queries and also the coarse-grained tokens which are relatively far away. Finally, it can concatenate the key and value token together for different granularities for computing the attentions. Based on the proposed focal attention mechanism, we introduced the focal transformers. It has a multi-skilled hierarchy and performs focal attention in each transformer layer. Based on the proposed focal transformers, we run experiment for image classification on ImageNet 1K. As you can see here, from the left side table, our focal transformer outperform the ResNet counterpart and also state-of-the-art visual transformers with different settings. As you can see from the right side, our focal transformer has much faster convergence speed than swing transformers. We also evaluate our model on object detection. Based on this result, we can see that our focal transformer outperformed the ResNet and also the vision transformers significantly on different settings. For object detection, we further evaluate it for different object detection methods. Clearly, our focal transformers outperform ResNet and swing transformers with large margin for different object detection methods. On the right side, we can see object detection with our focal large and multi-scale training achieve new SOTA performance. We also evaluate our model on semantic segmentation. As shown in the table, it outperforms previous SOTA with large margin. With our focal transformer, we lead 3 leaderboards in core vision problems, including object detection, instance segmentation, and semantic segmentation. We further do model inspections. We want to answer, do we really need both local and global interactions? As you can see from the left side, with both local and global interactions, our model achieved the best performance compared with the other settings with only local attention or global attention. On the right side, we can clearly see that the model needs both the local and global attentions. Finally, we visualize the learned relative precision bias in our focal transformers. As we can see from the first stage, we can see that the learned relative precision bias not only focuses on the short-range centers, but also the long-range regions. Similar patterns are also observed at the second stage and the higher stages. To conclude, in this work, we propose the focal attention, which effectively models the short and long-range visual interactions. Our focal transformers outperformed the SOTA vision transformers on 3 core vision problems and topped on 3 vision task leaderboard. Thanks for joining.